Alrighty, we have a do now right here. Do these three problems. So once I took the derivative of this one, I ended up with negative 2 sine of x. But if they're asking for the derivative at pi over 6, I simply have to put in pi over 6 for sine of x, which I know is 1/2. So the answer is negative 1. So the answer for that one, when you plug in this value, is negative 1. I don't have enough space to actually properly indicate it, but that will be your final answer for the first one. So let's do the second one. So for the next two, you just have to take the derivative, which was super easy. So the first one will just be this. I'm not going to bother expanding it because we already talked about the power rule. For the second one, the derivative of a cotangent is cosecant, negative cosecant squared. You have to obviously put the inside in, but then because since it is, by the way, the audio just kind of went away for some reason. So you put the inside in, and since it's chain rule, you have to multiply by the derivative of the inside, which is 3. So the final answer will be negative 3 cosecant squared of 3x. So today you're going to be learning about antiderivatives, and those are called integrals. For instance, if you have an integral of 12x to the third plus 6x squared minus 1, then you would pretty much find out what the antiderivative would be, or the derivative of what function would give you that. The proper way to do it is you add the number instead of subtracting, and then divide instead of multiplying. So it's pretty much the inverse of what we're used to when it comes to derivatives. So for 12x to the third power, it would be x to the fourth because we're adding 1 to the 3, and then divide by 4. So it would be 12 divided by 4 times x to the fourth. For the next one, we add 1 to 2 and divide by it, so that would be 6 divided by 3, and that will be x to the third power now. And then for the last one, we have negative 1. The derivative of what is negative 1? It would be negative x. Now, the important part is this one right here. For an undefined integral, it has a fancier term than undefined, but for a derivative that's not set in the interval, you have to assume that there might have been a constant, because the derivative of a constant is 0. So if you check this one out, if you took the derivative of this, you should get back to this. And the constant, the derivative of a constant would just be 0, which is why it would not show up right here. Alright, and then when you simplify it, when you finish dividing the stuff, you should end up with this. So let's do another example. So let's say we have this one. The integral of negative 15x to the fourth minus 16x cubed minus 8x. Now the antiderivative would be, what derivative would give you negative 15x to the fourth, negative 16x cubed, and negative 8x, and 0, because 0 we don't list. So for the first one, we would add 1 to 4, so that would be 5, and divide 5 right here, so that would be negative 3x to the fifth. If you took the derivative of negative 3x to the fifth, would you get back to negative 15x to the fourth? Yeah, you would. So same thing here. Add 1 to 3, divide by it, so that would be negative 4x to the 4. And then add 1 to 1, divide by it, so that would be negative 4x squared. And for the last one, we just say plus c. We don't know if that was a constant, so we just say plus c for a constant. Go ahead and try this one. See if you can get the antiderivative of this. Pause the video now, and then we'll look at it, and then you can compare it with what I get. Alrighty, so here's what I got, but I inserted a mistake. Can you spot the mistake? Dun 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 dun. Alright, the mistake is right here. This should have not been there. It's just x. When you have a 3, then that's the same thing as saying 3x to the 0. So you add 1 to that, and then divide by it, which would give you, oh, by the way, there's also no, the mistake's also right here. There's also no 2. So when you add 1 to this, and then divide 3 by 1, you should end up with negative 3 with an x. Well done if you've spotted the mistake. If you haven't spotted the mistake, shame. You're probably wondering what this would be. What's the antiderivative of 2 cosecant x times cotangent x? Now, if you remember your identities, this is not going to be a hard problem. So pause the video, see if you remember the identity. If you don't remember it, then look it up. Boom. Here it is. So if you remember, if you were to take the derivative of cosecant, where's my color? If you took the derivative of cosecant, then you would have got negative cosecant cotangent, and then you would typically have just the cotangent x and then plus c. But because there was a 2 up front, you have to respect that. And remember that there's a negative. So you do have to account for the negative. Now double check whether that's true. Take the derivative of this and see if you would indeed get the same thing what was up here. Here's another example. What's the derivative of negative 5 sine of x? So think of your identities and then try it out yourself. So over here, now we have 5 cosine, but because there was a negative, you have to cancel that out. The derivative of cosine will be negative, so that would kind of take care of that, and then plus c. Alrighty, just double check whether that's true. If you take the derivative of this, do you get this? And if that's the case, then you did it correctly. Alrighty, here are a few problems for you to try out. Go ahead and pause the video and try them out. I'm going to do a few of them, the ones that I think are difficult. Alrighty, good luck. So, all the derivatives look very straightforward. Even the ones that are, they kind of look like this. Because I recognize them. But the ones I do want to talk about is, first of all, this one, because that's like an inverse chain rule or something. So you pretty much add 1 to the 5, and then that becomes a 6, and then divide by it. But you have to account for the fact that if you took this derivative, you would have to multiply by the derivative inside, which is an 8. So you just attach a 1/8 in front to account for that. So you would end up with this antiderivative. Another one that I probably won't talk about is derivative. I mean, these two represent the same issue. I mean, this one right here represented that issue right there. But you should be able to figure that out. But 12 and 14 represent the same issue, so I'm just going to do one of them. I would say that maybe this is more intimidating than the cosine. Cosine is really comfortable. The cosecant cotangent, which derivative has cosecant cotangent in it? Oh. If you guess that cosecant is the one, then you're right. Cosecant, always on the wrong thing, and that's too big of a font, so let's make. So if you have cosecant, that's not how you do cosecant at all. Cosecant of x and took that derivative, so prime that, then that would equal negative cosecant of x cotangent of x, which reminds me of this stuff right there. The only difference is you don't have a negative, you also have a 2x, so that's going to be a 2 that I have to worry about. So let's give that a try. Let's assume that I'm going to think that cosecant of 2x is a good candidate for being its antiderivative. So let's take that derivative. So you would end up having a 2, a negative, and you would have cosecant of x of 2x, cotangent of 2x. That will be its derivative. Now I don't have a negative 2 up front, so I want to account for that. So I'm going to attach a negative 1/2, and that should take care of it because it's going to cancel out the negative and it's going to cancel out the 2. And that would be my answer. Well, this is the answer. Because now the negative 1/2 would get rid of negative 2. The derivative of this guy, just to make clear what I'm saying, the derivative of this guy is this. So the antiderivative of this is that. I speak in riddles. Yeah, I got 1, 2, 3, 4, 5, 6, 7, 8. I got 7 problems, but cosecant's derivative ain't one. All right, I think that's Okay, I need to stop doing stuff like that. Alrighty, so I'm gonna go ahead and present this again. Please do these problems and have them ready for when you walk in.